All right, so about computational microscopy. Up front, maybe for those of you new to Mathematica, let me just give the big picture just for one slide. Mathematica is a pretty big software to do all kinds of things. It's essentially, in its core, a programming language that you see here on the side, top left. Then it's a huge library of algorithms and mathematical knowledge. Besides that, it's a data source to provide data for all aspects of life, from your airline schedule to your DNA. Everything is under data sources. Then it has a system interface and a deployment mechanism to provide the functionality via the web, via your iOS device, for example, and so on. Furthermore, it has its own GUI, the notebook interface with dynamic elements. Then it has great visualization, graphics, and rendering capabilities. And last but not least, it's a typesetting system, a notebook that presents notebooks and documents. And today's vertical microscopy will be at home in several of these categories. It will have a good chunk of its capabilities under mathematics and algorithms, storing the image processing and machine learning algorithms that are applicable to microscopy. Then we do have some data sources related to microscopy. We will show some dynamic interfaces that are suitable for microscopy. And of course, we will have visualizations and graphics rendering the images that we get from microscopes. Okay, having said that, I like to quickly point out to those that maybe not in the field of microscopy, for whom it may not be a daily bread and butter thing, that microscopy is a huge area. For those of you new to the field, it may just give the idea that we're talking about light microscopy. And this would involve images like this, where you can have different ways of illuminating your specimens. You can have bright field, dark field, cross-polarized light microscopy, or phase contrast illumination. So even a light microscopy, there is a wide variety of ways to acquire images and to enhance image objects. Then there's just a huge array of other techniques besides light to obtain images. If you go to beyond the ordinary wavelength of light and go to, let's say, X-ray, you have X-ray microscopy, and this would be an example. If you go and substitute light by electrons, you have then typically transmission electron microscopy, which allows you to get extremely good resolution way beyond the wavelength that the light microscopy or X-ray microscopy can offer. Then you have techniques where you have, for example, confocal laser scanning microscopy, where you essentially scan an object. You don't just see it as a whole. This is an example here of a color-coded image of actin filaments in a cancer cell. See how it's being pulled apart. Other examples are multiphoton, or typically two-photon laser scanning microscopy. In this image, you see on the right-hand side, the red, the surface of a muscle cell, and on the left-hand side, some ligaments that are attached to this muscle cell. And just two more examples quickly. A scanning electron microscope gives you very sharp resolution. In this case, what you see here are pollen examples, typically then in black and white images, because what you essentially measure here is not light, but the reflection of electrons being kicked out of the surface of the specimen. And just because it happened today, I'd like to quickly mention cryo-electron microscopy, for which the Nobel Prize in Chemistry this year was awarded to Jacques Dubochet, Joachim Frank, and Richard Henderson. So we are, in a way, really up to date with our topic today. Well, of course, doing now mathematics, working in Mathematica or the Wolfram language and doing image processing, we are not in the business of acquiring microscopic images. That's beyond the scope. That's a hardware issue. But we are right in the subsequent workflow of microscopy, and that is loading images and digesting these images. That means trying to present them and then trying to analyze them. And if you go to a conference like M&M, that stands for Microscopy and Microanalysis. So essentially, we are working now here in this webinar on the microanalysis part of microscopy. That means we take in the images, filter these images. By filtering, I mean basically make sure that the luminosity is correct, that we may even do hyper resolution, that we try to quantify the colors, things like that, to basically make the image look good. Then a typical second step is, because the field of view in a microscope is usually very tiny, in order to cover any reasonable range on your specimen, you have to stitch images together, which means you take an image, you move, you translate your specimen, your object, slightly, take another image, and so forth. Essentially take an array of images and then stitching it together to a bigger image, so showing a larger area of your specimen. So that's step number 2, typically. Something, by the way, that can be done by many microscopes nowadays if there is an automation system built in. Then, well, essentially, I'd like to see what we acquired. So rendering images will be a topic today. Then once we have these images, we can reconstruct even more information that's usually in the images. So we can reconstruct, let's say, 2 or 3D versions of the image. We can then try to analyze the image, which means in the first step to segment the image to determine which part belongs to the object, which part belongs to the background, and so forth. And once we have an idea of what's what in the image, we can actually go ahead and measure and count object, or now lately, this is a new development, we can even try to recognize and classify specimens under the microscope. Okay, you already see that basically microscopy is a vast area that we will have no chance of covering in 90 minutes. So right now, and for this webinar, I pretty much focus on light microscopy. Some of the stuff I'm talking about can be easily taken over to other modalities of obtaining microscopic images. But for today, we talk about light microscopy. And the setup that we have in the company is pretty much what you see here. We have Zeiss microscope. Any other microscope will do. We don't want to push Zeiss here for that matter. And we bought a camera that we mounted on top of the microscope. In this case, particular one, we had a TubeTech camera. And this camera we address from our machine, be it a PC, be it a Linux machine, or in my case, a MacBook Pro laptop, and essentially get the images directly from the microscope. So the first topic, as I said, is image acquisition. Now, if you're a seasoned Mathematica user, you may very well know that we have a command called import that pretty much does exactly what you want. It just imports any kind of data, be it arrays, be it CBS files, be it images. And import will do mostly okay, even in image formats that are proprietary for some microscopes, because quite a few microscope companies just use TIFF, for example, a standard image file format, and just alter it slightly by entering more meta information and the like. So you may stand a good chance just to use import to read in your images that you may acquire from a microscope. If that is not the case, there is an endeavor called Bioformats, a website which I'm quickly jumping to now. Let's see. Yes, I get here the website. And they have 140 different formats that they support in the realm of microscopy. And for that purpose, we did come up with bioformats link packlet, which you can acquire from this GitHub here. So if we were to go here, you end up in this GitHub. You can download the content of the GitHub and generate a packlet that you then easily load into Mathematica. And once that's done and installed, all you would have to do is say needs bioformats link, and then you can load in data from whatever file format there is. In this particular case, it's an OpenLab live file, which I try to import here. And it tells me here essentially that I have 2 series in this file. If I now look at the meta information, I should get an idea of what kind of data is in there. Now what I get here is an XML format for the data, which is easily parsable. So if you write a code to look for particular information, that's possible. For my purpose here right now, it's sufficient to convert this into a string of XML code, and that is barely readable, I guess. So looking at the data, I have here a first sequence called embryo number 1. It's data encoded in big endian format. It has XYZ CT dimensions format and so forth. It has 1 channel, just 1 time instance, and this is the size in X, the size in Y, and the size in Z or maybe T. Furthermore, it is encoded in 16-bit data integers per channel. And then we have a second run here, which is encoded in just 8-bit units, so 1 byte per pixel, and it already is a 3-channel image, so color image. So I will resort to the second sequence here, go import the last sequence or the second one, and essentially this will be in the list, so I just want to have the first part of the list, and this will generate here a sequence of images that I can look at using manipulate. And you see here it's a fluorescence microscopy image that shows the cells of an embryo under division in some parts, and I can just go through the whole sequence of images, essentially images, a stack of images making up a volume. Okay, if you were to be cooler, which unfortunately I can't do right now, you may want to consider using library link to connect to the API of the microscope or just the camera of the microscope, which would enable you to read images directly into current image, or even, if you take the time, may enable you to steer the microscope remotely. Unfortunately, the microscope we're working on is on the other side of the Atlantic right now, so I cannot demonstrate this. Besides, this will be slightly different from microscope vendor to microscope vendor, so I'll skip this step. So assuming now that all the images are in the system and we can proceed and apply all the image processing capabilities of Mathematica, or the Wolfram language for that matter. And I'll just pull a few of these things applicable to microscopic images out of my head. The first one would be to apply tone mapping to HDR images. HDR stands for high definition range images, so basically images that not just have 1 byte per encoding per pixel and channel, but a deeper encoding, which allows it to store more luminosity values, more than typically ordinary screen can render. So your eye has the capability to adjust to lots of light intensities, and that allows us to also see details in the dark or details in the very shiny parts of our everyday life, but not necessarily in images. So what I do here is I now take the first block or the first sequence of data from the file I just was about to import. There we saw it has a 12-bit encoding. So what I do now is I encode here the whole data set. It essentially would be a 16-bit encoding because it's the next bigger encoding scheme in Mathematica or the Wolfram language. And then I can look at the data, but since my screen only has 8-bit rendering, I do color tone mapping, which allows me basically to adjust to the brightness appropriate to the image data. And you can see that you can, well, I hope you can see on your screen as well, that you can see much more detail in the fluorescent microscopy images than you just saw in the previous slide. Well, this basically adopts the luminosity of every channel separately. I have here now the color tone mapping in R, G, and B. If you don't want to distort your color perception, you may want to do the following. You want to do color tone mapping just based on luminance. This will not alter the mix of red, blue, and green. And you may not get as radiant colors, but you may at least get the correct mix between the red, blue, and in this case, I don't think any green fluorescent markers. Okay, so this would be the first step or example of filtering incoming data from your microscope and utilizing built-in capabilities in Mathematica. As I mentioned, the images that you typically get only cover a very minute area on the specimen. So typically you do not read just one file or one image in, but an entire array of data. And what I have here, just to give you an idea, is an array essentially of 4 times 4 images depicting images of a DNA strand. So this is just a small excerpt. And in order now to put it all together, I have here a little command that is in the appendix of this talk, which you are free to download, which essentially stitches all these arrays together. Essentially, it is image align, but since I only have a small overlap between images, I did have to write a small program to do this currently correctly in Mathematica. If you're lucky, the microscope will actually do it for you. And in this particular case, what we get is the following. As you can tell, image stitching is a tedious task, and it takes a while. Okay, and this is the result. So you see now a much bigger portion of the DNA strands on your objective. Now, what you may also notice on your end, on your screen, is that I have here some vertical and horizontal shadows in the image. Now, this is typical because what happens quite often is that the luminosity, or the illumination rather, of your specimen is not nicely homogeneous in all corners of your field of vision. Typically, it tends to become darker at some corners. And that's exactly what's the case here. I get this tiling in a way because the images tend to be brighter in the center, in this particular case, than on the boundary of these images. So one other typical task in microscopy is brightness equalization. Brightness equalization, well, is necessary for stitching, as you just saw, but it's also nice to have because if you are in a later processing step, if you get ready to do just thresholding, then thresholding would very much be hampered if the illumination of the specimen would not be nicely and homogeneous. So doing brightness equalization at right up front in your pre-processing pipeline is always a good idea. And since that's the case, we came up with a dedicated command in Mathematica, which is called brightness equalize. So what we have here is an image. In this case, I think these are just salt or sugar crystals. And if you were diligent enough, you may have taken an image prior to placing the salt crystals or sugar crystals under the microscope. So you have, in a way, a ground truth with respect to the lighting of the microscope. And you can already see here that the illumination from beneath is not quite homogeneous. Now, if you have such a sample, such an empirically obtained so-called flat field, brightness equalization is pretty easy. You just take the image, you take the flat field image and place them both into brightness equalize, and what you then obtain is an image where just the lack of light in one corner is taken out or is actually substituted, whereas the more of light in the other corner is taken away. And so this original image at the end should look like this. And just to see the, well, somewhat subtle difference, I'll flip forth and back. Okay, and having done this and just redoing the image stitching that I had done in the previous slide, I quickly see if this works now. I do have here the flat field of those previous images, and this should now, and it does, give me a nice even image without any tiling effects due to shadows in the illumination. Okay, so this is the brightness equilibration step, except one quick addition to it. It very often occurs that you do not have a chance later on to obtain a flat field directly at your microscope because the conditions may have changed. You may not have taken the images yourself. So quite often you are doomed to actually generate your flat field posteriori, and that means basically taking the image with the specimen in it already and trying to derive a flat field image. And you can do this here by generating a mask that takes out the, or just leaves the background in and takes out the foreground. And then based on the background, you can tell brightness equalize to model your background with a very stiff model, let's say just a plane, or in this case, a global polynomial of second order, or any order you like. And again, here we come with the result, and you see it's almost just as good as having taken the flat field up front. Okay, so not a very exciting, but in a way necessary step in the early pre-processing of microscopic images. Now I'm looking at a very specific kind of microscopy, and that is the staining of tissue with stains. There are all kinds of stains that are indicators then of certain properties in your tissue, and especially they also make the tissue, which can be very transparent, much more visible under the microscope to begin with. But mostly at the end of the day, you not just want to know or have nice colors in your image, but you also want to measure the uptake of stain or of the dye that stains your tissue. And for that matter, you have to translate the color in your image into the concentration of dye uptake in the tissue. Now in this case, I have hematoxylin and so-called DAB. Please spare me here these words. I'm not very good at pronouncing them. Anyway, I have these two dyes, and you can look up in the literature the exact color of these dyes, and that's exactly what I have read in here. I have taken the RGB values of hematoxylin and diaminobenzidine. And once I have these, I can look up the RGB values and obtain basically a matrix that takes the concentration of these dyes and converts them into RGB values. So this would be the matrix. But essentially what we need is not this matrix, but the inverse. So we have to take the pseudo-inverse, and this will now take from the image above the RGB values and convert them to my H or DAB densities. Now, we have to be aware, though, that dyes are basically shielding the light or hampering the light from shining through the specimen. And they do that in an exponential fashion. So if there's only very little dye, it goes through very nicely. But if I double the concentration of dye, the color or the decrease in light or colored light going through will not be just double, but will grow exponentially. So for that matter, we cannot do this color demixing. That's essentially what we are going to do here in the color space of this image, but we have to first transform it into a logarithmic space, into a space with a logarithmic scale of color intensities. Then we can do the color remixing or color mixing, demixing essentially, and then we can project everything back. So this will bring the colors of the image into the logarithmic scale. This will essentially perform the demixing. I'll do an image adjust so that I have everything in a range between 0 and 1. And then I can just combine these concentrations of the different dyes back. Well, wait a minute. I didn't want to take this image. I wanted to take this image. So we go back. I can translate now these images, which basically represent the concentration of the two different dyes, and construct an image of false coloring that gives me then a much more realistic impression of about the densities of the dyes, because now the dyes are purely red, and in this case purely I think green for the second. Yeah, well, actually it's green and blue mixed, so cyano coloring for the second, for the GAB stain. And this then allows you to do calculations on the image. You can actually quantify, or at least quantitatively get a qualitative idea of the dye uptake in the image. So the whole process, by the way, in case I haven't mentioned it, was called color demixing, or sorry, color deconvolution. All right, so once I have now the image in the machine, I have pre-processed them, I have basically what I want to see extracted from the image, I'd like to view it. And we have seen already that quite often you stitch images that are by themselves already pretty big to even bigger images together. Well, I just load here a big image, which is not that terribly big, but it's a big image. Whoops. So URL download. I'll just do it. Well, I'll just do an import that way. Well, the point here was I can, what I just did here, I just uploaded a file, and now I just have a file pointer or file name essentially at hand, because the following command, which I'm about to introduce to you, dynamic image, can display in-core images, that means images that are in the memory of your computer, or out-of-core images, that means very large images that may not even fit into your memory. And dynamic image then would just read the portion of the file that is available, or that is needed to visualize. And let me quickly actually import, because this will make the following a bit more responsive and easier to show. And okay, what I wanted to do was to show the image quickly. And you see here, it's a pretty big image. And if you have a large screen and the notebook is large, you may actually be able to view it in your notebook. But quite often, it's such a big image that you may not see the detail if you have a global view of the image. And that's when dynamic image becomes in handy, because dynamic image functions just like an image pane, where you can zoom in, where you can pan around, basically where you can look at any portion of your image. First of all, you can just resize it any which way you like. And then you see on the side some awkward looking scroll bars. They allow you to scroll to any position. But not only that, they have these knobs at the end where you can actually zoom in by making the scroll bar smaller, or zoom out. And so the scroll bar even gives you a kind of first-hand indication where you are in the image and how large your image excerpt is. You can pan around in the image. You can hit the zoom button to go further in. You can hit the zoom button to go further out. So essentially a nice tool to view images that tend to be large. But it's more than that. it's a very nice tool to create interactive means to measure or interrogate your image. So what I have here is some code which shouldn't scare you away. It's actually a very potent code. So very few lines for what it actually does. What it is it's a little dynamic image, essentially here, that to which I now attach a tool, a circle, with which I can measure circular objects. I do it as follows. First of all, the outermost construct is a dynamic module to provide some local variables, the radius of the circle, the center of the circle, initially at the center of the image, and here's some Boolean token that tells me if I'm moving the center or not. And then I put all of this in the panel, and the content of the panel is handled by an event handler that, for one thing, shows the dynamic image, which is the image itself, and some text on the right top, on the left top corner that will display R, or the value of R. Furthermore, it then has in the event loop, or it screens for the following events. It looks if the mouse is down. If so, if the Command or Alt key is down, it will measure the distance between the center and the mouse. If the mouse is close to the center, it will assume to move around the circle itself. It will move the center of the circle. If it's further out, it will actually not move the center, but the radius. And that also holds true here. If you drag the mouse, you don't, in one case, you alter the position of the circle. In the other case, you change the radius of the circle, depending where your mouse is, in the center of the circle or close the boundary. And if I now evaluate this, I do obtain some remark, but well, this argument. Okay, that's why I didn't make here. What was original? It was URL download. Sorry, I have to get this because this was now programmed to handle just a file, because it just imports the file on demand. So I have to do it once again. Okay. Okay, so what I see now is again dynamic image. I can do all the things I have done before. I can resize it. I can zoom in. I can zoom out. And I now have here a circle, a tool, which I can access not by just panning or zooming, but by holding down the Alt or Command key on a Mac, and then I can move the mouse around or the circle. I can alter the radius and take here, for example, a radius measurement on this particular pollen that tells me, in this case, it's a radius of 92 pixels, which I then, knowing the pixel size, would have to be able to translate into the actual size of the pollen. Now, this is quite often necessary, so if you have some manual tasks that you'd like to do, this would be a way to install it in Mathematica in the GUI. Okay, so much for interactive work in Mathematica. Now we look at some more extravagant image processing features that we have, and one is focus stacking. Now, before I explain what focus stacking is, I will bring up a scenario that you may be very well acquainted to working with a microscope. Now, working with a microscope, and you have, in this case, a pollen under your lens, you may notice that trying to get the thing into focus, you don't achieve that everywhere in the image. You can zoom in or move up the focus or down. You will always tend to just have a small portion of the object in focus, and the other part will become out of focus. Now, that is of no surprise if you think about it, because your depth of field is extremely shallow on a microscope, which also, by the way, holds true for macro photography. So the plane in which an object is in focus is very, very thin. In contrast, if you take, for example, ordinary photography and have a telelens, then the field, the depth of the field where an object is in focus may be really pretty big, maybe a few hundred meters wide. Under microscope, it may just be a few micrometers thick. So essentially, if an object is thicker than the depth of the field, then you are out of luck. You cannot get everything into focus. But actually, it's a blessing, not a curse, because what you can do is you can take a whole sequence of images, all with a different focal length, and stack them up. And this is then called a focus stacking. And such a stack you can provide to command a mathematical called image focus combine, which then allows you to just extract only those portions of the image that are in focus and then go to other layers in the stack to get more pixels that are in focus. And essentially, you then get an entire image that is in focus for the object you're looking at. Now, well, we could just quickly rebuild it. Now, I don't do this for the fun of it, but I'd like to bring image focus combined to a different level, to a higher level even. I want to be able to reconstruct the 3D information that's in the focus stack to construct a 3D model of the specimen. Now, quickly, how does image focus combine really work? Well, essentially, you have to have some feature in your image that tells you if you are likely to be in focus or not. Essentially, that means if you're in focus, you should observe sharp edges. You should have sharp image features, and that would imply that you have high spatial frequencies in your signal. Now, high spatial frequencies can be detected with a Laplacian Gaussian filter, because essentially it's like a filter that locally measures the frequency. And depending on the scale of the Laplacian Gaussian filter, it picks up higher frequencies or lower frequencies. And if I now just take here a Laplacian Gaussian filter at a fairly high resolution, that is here basically at pixel resolution, then this should give me only a strong signal if the image portion at that part is in focus, and the response of this filter should decay fairly rapidly if something gets blurred and out of focus, because high frequencies usually are subdued the most when you blur. So what I do here is I create a focus response, and you can see very nicely here, if I do this with the focus stack that I had in the previous slide, I can see that if I move through the stack up and down, that different portions of the image come into focus and go out of focus, just as I had perceived looking at the image. Now, I can basically, now this is just a volume of responses. I can do what's called a non-max suppression filter, which basically means if I look at a column of this stack, I only want to keep the response that's maximum. I only want to get the pixel in the stack that has the highest response with respect to this Laplacian Gaussian filter, because that pixel should be the one most in focus. So what I do here with these two lines, I basically kill all other responses except the maximum response. And if I now multiply that with a stack and add up all these images, essentially I get the result that I just got with image focus combine. I get the assembled image with only those voxels in the stack that are in focus. Now, this depth volume, however, as I mentioned, should give me also information about the depth of the surface I'm looking at, or the distance for that matter. So by extracting the length or the Z component of the pixel that is in focus, from that volume I should get a so-called depth map, a map that tells me roughly how far away a pixel is. And this is such a depth map. Well, first of all, where I have no object, well, it appears to go to infinity or stays at 0. So this white area is basically an area where I don't have any information. Here, however, I can see that in the dark area, these are pixels far away. And as more as I get to the center of the pollen, I see that I have here pixels that appear to be very close. But then I also have pixels in between that don't really make sense, a lot of noise apparently. And that's to be expected because you can only measure if something is in focus or not if you have an edge present. So if you are in an area where there is no edge, then this depth reading may be completely unreliable. So what I have to have is I also have to have a confidence map that tells me, is this depth reading reliable or not? And this is just, again, the focus response, because wherever I have an edge, which the Laplacian filter will pick up, then I have a reliable reading about the depth of the pixel, otherwise I don't. So I just take now confidence that is above 0.05 into account. Furthermore, I do take a median filter to a little bit take out the noise, and then to fill the gaps, I do a filling transform. And essentially, I come up with here with this kind of depth map that is much more regularized than the original version, and that should give me a good-looking result once I now reconstruct a 3D object. And I do that in the following way. Essentially, I just do a list plot 3D of the depth map. This should give me basically a 3D mountain range, or basically elevation range, of this object in the Z component. But on top of it, I'd like to see the original image displayed or projected onto that mountain range. And I do this by taking the texture of the in-focus image and setting the alpha channel to the depth map, because essentially where there is no depth, I don't want to have anything projected. Okay, and once I do this, I very quickly get now our 3D model just reconstructed from the lack of focus, or due to the fortunate fact that the depth of field is very shallow, and that this helps me to actually even gauge the Z component, to measure the Z component of a specimen, not just to visualize the X and Y component. Okay, now this has been an example of reconstruction to visualize things, to make it more susceptible to the human eye. But quite often I also have to measure or quantify or even classify what I see under the microscope. And this brings us now into the realm of machine learning and into the realm of neural networks in particular. Now, the task at hand, which I'd like to show you in order to explain what we have, is as follows. I basically collected pollen from my garden. Well, this is a white lie. I actually got it from the internet, but strictly speaking, all these pollen do occur in my garden. I have tulips. I have poppy seeds. I have lavender. So basically, I have all these flowers that you see here, and I basically have of every flower a sample of 6, 7, at most 8 pollen types or pollen samples, and a total of 6 different types of these pollens. Now, there are big dictionaries in the internet, also accessible for purchase, where you can look up pollens that you may have under your microscope in order to identify them. But this is a very, very tedious task, and something you definitely would like to automate. And this is an example how this could be done. Now, you may have heard that if you do neural network training, you have to have tons and tons of data. In essence, it's correct. You have to have lots of data, because a neural network essentially is a function with thousands or even millions of parameters that need to be fitted in order to achieve the task at hand. Now, as you have seen, let me quickly go back. I have everything but thousands and thousands of images. I just have here 6 times 6, maybe something of the order of 40 images, which definitely does not qualify to train a network from scratch. But one can do something else. Just like a human being who doesn't have to learn how to see from scratch, but utilizes on all the image data it has seen as a toddler, I can also utilize neural networks that have been trained on other images of, let's say, houses, trains, seas, trees, animals, whatsoever, and transfer the knowledge gained in these models to the task at hand. And this particular technique is called transfer learning. So what I'm doing here is I load now from our repository of pre-trained neural networks that is attainable under NetModel. Whoops, why is it now spinning? Well, essentially, I have retrieved a neural network and stored it under net. It is a somewhat famous network type. It's called a VGG16 network, essentially 16 VGG layers. And this network structure was trained on a huge data set of images on the ImageNet competition data. And for some reason, loading this network has stalled my front end, and I may have to do some drastic measures to regain control. So please bear with me. I'm now killing Mathematica. And restart it. So I have to find the window again. Here we have it. Okay. All right. Let's hope I'm back in business. Okay. Let me go to pollen classification. Here we were. Okay, so I enter the data, and yeah, well, I have to go through this. This is loading some data in, which I will need later on. Unfortunately, this will take a minute or so. So let me just explain what I'm about to execute here. So this is the data that I'm going to need. Hopefully, this cell has been activated. And if I now move on to the next slide, I have pointed out that I load a pre-trained network. And then what I will do with that network is as follows. I will cut off the last few layers in that network, because the assumption here is that the network trained on images has learned how to extract certain image features in its first few layers. And then at the end, when it was asked to classify the content of the image, only the last few layers it was working on the classification itself. Now, I'm not interested in the classification of this network. I'm just interested in extracting image features from an image. And for that, the first part of the network should be sufficient. Okay, I'm back in business, so let me evaluate this here. Get the network. Okay, I'm still there. And truncate the bottom part. Okay, you can see now that I did cut off here at layer what's called FC7. It's a linear layer, so-called fully connected layer. I won't go into the detail now about neural networks. That will be beyond the scope of this particular webinar. And essentially, I will just copy here all these convolutional layers that extract somehow some relevant information from an image. And this now will be my last layer, linear layer, and this will be a layer of 4096 or 4K dimensions. Now, what does this network do? Well, if I apply this network now to a training set, it will essentially run every image through the network, and then for every image it will generate a vector of 4K dimensions, so 4,000 dimensions. And that in a way should hopefully capture the essence of the image of whatever I want to do with it. So this is just an excerpt of this very large vector for just the first image. First element is -4.7, last one is 1.47, and there are 4,094 different values in here. Now, unfortunately, I cannot visualize a feature space of 4K dimensions, but I could use, in this case, dimension reduce to project these 4,000 dimensions down to 3, just to get an idea how this feature space looks like. And what you can see here with this projection is that, yes, apparently it does group the pollens in this space, so that apparently the features do catch up some entity of these pollens that allows me to group them. And if I can group them, I can also classify them. You can very nicely see this group of pollen here, this group of pollen here, and so forth. So it looks good. By the way, this dimension reduction is called T-Sne method. It essentially basically tries to project the data down by preserving neighborhood relations of the data in the high dimensions. Okay, so being positive about being able to classify now with this feature space at hand, I do one trick that you can always use if you have very little data. You can generate more data. And this is a small command in Mathematica that I just implemented. It basically takes a pollen image and just rotates it, and also takes the mirror image, so making 8 pollens out of 1, which is good for training. And then, well, what I do here is I essentially increase my training set from around 40 to 40 times 8. And then last but not least, I won't even go into the details of creating neural networks. I'll do that in the next example. I just use here the built-in machine learning command classify, which will automatically select an appropriate classifier, be it support vector machines, linear regression, or neural networks for that matter, and it will try to classify this set of data. Now, I won't wait for this because time is flying by. This will roughly take a minute, so we can save the time, not wasting it. It will generate a classifier function, and if I then take this classifier function, which I called here pollen classifier, and apply it to a completely new set of pollens that have not shown the machine during the training phase, I can actually run it and get proper classification all the way through. Now, this, of course, is a very small set. I don't really can quantify the quality of this particular classification, but it's a first good step. And essentially, at the end of the day, when you do these kind of classifications, you may not want to be able to classify one pollen at a time, but it helps to have several pollen of the same type in order to do a fairly specific, fairly robust classification. Okay, so this was in a way a toy example, and now we zoom in on a really, really challenging, hard problem. The problem at hand was given out by the Technical University of Eindhoven in the Netherlands as part of the so-called Tumor Proliferation Assessment Challenge last year. So how does this challenge look like? Well, you're being given these tissue samples. These are samples of breast tissue, and the task at hand is that one should try to count, or first of all find and then count, the number of cells that undergo mitosis. So that basically undergo cell division. The idea behind it here is very simple. Cancer cells tend to divide far more often than ordinary cells, and if you have a high mitosis count, then that's a clear indication of having a malignant cancer in your tissue. The problem, though, is finding cancer cells or finding cells undergoing mitosis is much harder than it sounds. Well, these mitoses don't come in very nice in cells that very nicely show two nuclei or a nuclei about to be divided. No, the data essentially looks like this. This is part from data taken from this larger screen via ordinary image processing methods. Essentially, I just focus in on all these black spots that look like nuclei that could undergo mitosis. And then having just cropped all these little cells, I then look in more closely, and hopefully now with a neural network, will be successful by telling that this particular nucleus undergoes mitosis. In this case, it's false, but this particular one, at least according to 3 pathologists that did the screening and that came up with a ground truth, or what they believe is a ground truth. This one is an example of mitosis. This is not. Here again, I have mitosis. And even if you look at these images, at least personally, I have a very hard time actually telling at all what's mitosis and what's not. So this is definitely not a toy example. And what we have here now are 1,800 of these cropped images, fairly with a mix of 50-50 or 1/3, 2/3 of cells undergoing mitosis and those that don't. Now these are, as you can see here, so-called labeled data sets. That means every image comes with a label that says, yes, this is mitosis, or that's not. So the machine doesn't have to find out what mitosis is, it just has to learn how to recognize it. Now, how do we do this? Well, we construct a neural network, because neural networks have proven to be a really, really versatile and also very flexible and powerful way of constructing classifiers. Classifiers that not only classify a feature space, but that also, in very many cases, generate the features themselves. By that I mean is you apply the neural net directly to the data. You don't have to run some kind of feature filters in between. You don't generate a feature space. That's all done within the neural net itself. Now, neural nets, in order to do so, tend to be models with plenty of parameters. Okay, so this is a very rough idea or depiction of a so-called convolutional neural net. Convolutional neural net essentially, in this case, starts here on the left-hand side with a so-called an orange layer. And in essence, what you would do is you take the image. In our cases, there were images of 97 times 97 pixels, and the activity of each pixel is basically transferred to the activities of all these neurons, to the array of neurons of 97 times 97, and in the case of RGB images, times 3 neurons. And then, just like in the brain, you have axons, you have connections to the next neurons. And the idea is that you could, in principle, connect every neuron with every other neuron, and that every connection could have a weight that would be as a synaptic connectivity between those neurons, and tell if the activity of one neuron is well transmitted to the other neuron or if it's blocked. And these weights, or these different transmission capabilities, they are the parameters in my system, and the more connections I have, the more parameters I have. Now, in order to avoid an exorbitant number of parameters to learn, what we do here is we have a convolutional net. That means that in the next layer, only the neurons in the vicinity, for example, here on the top left corner, connect to the neurons in that corner, and so forth. We would just move on. Then we would have a next group of 3 times 3, 3 times 3 neighborhoods that then connect to the next layer, and we won't connect everything with everything. And this very much resembles a kernel that moves along an image in a convolution scheme. And that's why these things are called convolutional kernels. In essence, a neuron in the second layer collects all the activity in the first layer or the previous layer. That's what this layer does. It basically collects, like a convolution, the activities. Then I may want to normalize the activity to avoid spikes that go beyond the range of what's reasonable. Then I have to have what's called a nonlinear component, because every cell just not linearly passes on its activity, but it has a threshold under which it stays dormant and above which it becomes active itself and then would transmit that activity onto the next layer. So we have a depiction of well, here only two convolution layers. In essence, down here we have a network with 1, 2, 3, 4, 5 convolutional layers. And then we do something that's called flatten. We basically give up these two-dimensional grouping of cells, but just stretch it out as one long vector and then connect every neuron with every neuron. That's a so-called linear or fully connected layer. And at the end of this whole ball game, we have a so-called softmax layer that takes the activity of the last cells and just basically normalizes them so that the overall activity in essence becomes 1 and that the activities can be interpreted as probabilities. Now, if every cell here is a probability for a certain statement, then you have to have as many neurons as there are statements in your model. Now, we just have 2 statements. We just want to know if the image under observation is undergoing mitosis or not. So we end up here with a linear layer of just 2 neurons saying, yes, we have mitosis or not. And then the whole network basically specifies an encoder. That means the activity that goes in are images, color images that are being then translated into arrays of neural activities. And at the end, the probabilities that go out are essentially as a class statement, a class of mitosis being present, and the 2 states are just true and false. So, okay, with all this explanation, I now enter this net chain, the simple neural network in Mathematica, and I go further. I now train this whole set. I train the network with nettrain. This is a network. This again is a training set, which I again enlarge by rotating and mirroring the incoming image. Then I have a validation set. You may wonder, what's a validation set good for? Well, essentially what I do here is fitting. It's fitting just like fitting a polynomial. The problem is I can, in principle, overfit. That means I can take bizarre properties of the data, maybe noise, and just make sure that my polynomial or my learned network reproduces that noise. But that would be overfitting. So I just want to make sure that I learn with my network the essential properties that allows me to predict. And then I predict not on the data set that I have learned, but I predict on a data set that I have set aside, the test data set, to see if what I have been learning actually amounts to something. And then what I can do is here just run this, and this will fire up the neural network that I run here on a GPU. In this case, it goes very quickly. It takes less than 10 seconds. And what you saw there, I quickly depict it here, I haven't frozen this image quickly, is the decay of a loss function. Now, so far you haven't seen a loss function in neural network. Basically, it's just a function, a cost function that tells me, is the neural net working well? Does it produce the output that I want, that I have there as labels? Or does it come up with some output that deviates from the ground truth? And that loss function is basically the red line. We see that the network learns, and becomes better and better in forecasting the label. Except that here the blue line is the one that actually is the test data. And when it then the network is applied to the test data, it doesn't do so well starting about at this point, which means it learns, but here it starts to overfit, and the result, the forecasting power of the network will stay at a level that seems to be mediocre, but we'll see. Okay, so we have trained the network. Now we can use classifier measurements to quantify the quality of this machine learning apparatus of our neural network. And one way to quantify it is to calculate the confusion matrix. Now, the confusion matrix essentially tells me how often I have classified mitosis true when it was true? How often did I classify it as true when it was not true? Well, apparently this didn't train very well yet. It's almost 50-50, a slight bias classifying it correctly. But at least when it was not mitosis, in very few cases, I only accidentally had a false positive. All the other ones, cases here, 432 cases, were classified correctly. So if I combine this into a measure of accuracy, I'm accurate almost in 90% of the cases, or put it differently, I have an error rate of roughly 10%. Now you may say, well, this looks bad, but if you were looking at the pathologist who generated this data, there were 3 people doing it, and they didn't agree very often. So estimating on their performance and how often they agreed on what they were marking as ground truth or not, you can estimate that 10% is a very reasonable value and comparable to what a pathologist may achieve by themselves. So this is in a way a success, even though it looks somewhat mediocre. It's not as shiny, but this is a real-world example. This is what you can actually achieve out there. Okay, now we have almost all the time used up. We wanted to reserve about 15 minutes for Q&A. So what I'm going to do now quickly is to show what's already possible if you really push the limits of deep neural networks. So for one thing, we have a deep neural network in our network model that is trained on a gigantic data set of images. This is the network that we also use for our internal command image identify. So if we load this network, this is how it looks like, and apply it to an image like this, it should come up with the correct answer. And yes, it even says this is a beagle. So what more can you want? This is not just even telling me it's a dog. It even says me what kind of dog. And since it got even better now, this is redundant, this example. Even if I confine the whole classification to the sub-regional subclasses of dogs, it gives me the correct answer. And we can even verify what the probabilities were, the activities of the neurons that were standing for the different classes that were reasonable in this case. Well, beagle was sure for 99%. That is a hound, which is even a bigger class, was close to 1, same for hunting dog, and it was most definitely a domestic dog. And you can play around with image identify not only in Mathematica or the Wolfram language, but also on the website imageidentify.com, and try and test our network and see how powerful it is. Now, you can extend this, you can apply it to people, and in this case, it tells me it's a person. Now, you may say, well, this could have been better. This is a notable person. That's true, but if you want to have notable person, and if you actually want to distinguish between famous people, you would have to call up a network that has actually been trained on famous people. And so this would be classified on a pre-trained network called notable persons, and it will call up this network and hopefully come up with the correct answer. Yes, it is Barack Obama. Now, okay, this looks like a politically incorrect statement, but let me quickly explain. I don't want to make any kind of false impression. What I'm trying to do here is the following. In a way, it's well known that a dog owner tends to have a certain resemblance to the dog he or she owns. So if I want to build a kind of dog breed chooser command in Mathematica, I could do it as follows. I could use image identify, take an image of a potential dog owner, and say, yeah, please identify this person as a dog. Now, this should get the dog with the closest resemblance to that person, and that may be then the best breed to get. So let's see what kind of dog Obama should have gotten. Takes a minute. And here are the odds. Miniature pinscher, 83%, pinscher in general, 83%, guard dog, still 84 in general, but then here, well, these are already fairly low probabilities: Hungarian pointer, greyhound, Italian greyhound. Well, these are the choices, and obviously it's a pincher that we recommend, but this is a fact of life. Machine learning can go wrong as well. It's not foolproof. And here you have it. Obama didn't get a miniature pincher like this one, even though this guy has a certain resemblance. He actually bought a doodle, a mixture of a Labrador and a poodle. Okay, so that was image identify. Now some other example quickly that may relate very well to microscopy, because when you do microscopy, you generate images, and usually you generate a large amount of images. And if you don't tag these images with respect to their content, you may have a hard time retrieving images, finding images that may resemble the current specimen that you have under your microscope. So a possible scenario may be that you want to do image retrieval. You're given an image, you create features from that image, then you look in the feature space of your database. Is there any other feature vector that resembles it, that it's close? And if so, get the corresponding image, and that should, if everything is working correctly, should be an image that resembles the original. So without any tags, we should be able, with a neural network that generates these features, be able to obtain feature vectors in a data set and then retrieve the corresponding images. So I do this now very quickly, not on microscopic images, even though this would be readily possible, but I do this on dog images simply because dogs are more easily recognized by everyone, whereas you may have to be an expert on certain tissue to see the difference. Okay, so what I've done here is, I loaded a neural network, cut off at a certain layer. In this case, I cut off at global layer pool here, so right beneath layer 5B. This will generate a feature vector through this function feature extract. It takes an image of 224 times 224 pixels. And so I have here now a data set. For every image in this data set, again, I create feature vectors. So this is what I do here. I create a nearest function based on these vectors in the, and then I have here a command nearest dog that basically takes an image in, extracts the feature, looks for the nearest feature vector in my data set, just takes a first case and renders the image with that corresponding vector. And now we just do the test. We have here 3 cases, a Labrador. Let's see if I get another Labrador in the data set. Yes, it extracts it very nicely. Here, a little dog, and again, a poodle, or doodle rather, and you can see you can retrieve images even without having pre-built any of these tags, but just running feature extraction. And by the way, I did manually even generate my own neural network to create feature vectors. There's a command in Mathematica called feature extraction that may be just applicable for your particular problem without having to do all what I have done here. All right, this unfortunately already concludes our webinar, at least the presentation part. I hope you liked it, and I hope you see now the Wolfram language to be applicable wherever you go. At least we see, even in a way, our spiky, wherever we look. This is a spiky pollen that we had under the microscope the other day, and it has a certain resemblance with our Mathematica logo. Thanks for listening. I will now surrender the screen to my colleague Shadi, and she will start with a Q&A session, and I may kick in later on and take over a few questions. Thank you.
Thank you very much, Marcus. I hope everyone has enjoyed the examples that we have shown. As I said to a few of the questions, this was just basically a collection of few examples to give you a sense of what can be done with the Wolfram language, and we hope you get good ideas for how you can tackle your problems using all of the capabilities we're providing. Note that the image processing capabilities of Mathematica has been there since version 7 and is fairly well developed. Everything neural network is fairly new, and well, actually both sides of it, both image processing and neural network, is still under very, very active development. But I think more for the neural networks part of our development, it is actually under even more active development. It is still not a very mature sub framework. Everything is evolving in the field of neural networks even, not even talking about Mathematica. So look forward for more advancements, more features, and more automation in that domain as well. A few of you asked about the data that was used for this webinar. Examples that we use, some of them we don't have permission to redistribute them directly, but we will make sure if the links are not in the version of the notebook that you received the download link for, the notebook that we will send after the event includes all the sources for you, all the links to download the sources from the web. Yourself. Anyways, it's big material, so you can. It might be even easier to send them separately. There were questions about courses. We do have a paid, or actually sometimes I think we have it online, course on image processing. If you just search for image processing course, I had this open, close it. Under instructor-led courses, you'll come here and there is a fairly extensive course on image processing. Similar courses are also being developed for neural networks. Apart from that, we have a variety of pre-recorded events that we have had in the past, specifically on neural networks, specifically on image processing using neural networks for generic applications, not necessarily for microscopy and so forth, that you can probably access most of them from Wolfram UNA. There were, okay, on the question of how we can highlight, how we can handle batch processing of large image files, I would like to mention two functions that are recent in the system, file system map and file system scan. Similarly to our functions map and scan, one applies the function f to all the files given in that root and then returns the result. The other one scans the file and then just basically works by side effect. So if you want to print something, you actually have to say print this or print that. Two examples that I put together quickly for file system map using that same one of the data sets that Marcus used the DNA data. I'm here importing the files one at a time and doing some measurements, in this case a simple mean intensity, and then yeah, I probably had to do the same file name forms TIFF so that it doesn't look into anything that is not a TIFF file, and put together a data set with file names and the computed mean intensity. This is basically doing some measurements on the file. However, we can also do something like import the file and do any operation like a simple color negation, and then specify a file path to export the result to. And in this case, if I basically run that command and go to my Finder, which I don't seem to be able to find now. Let me see. Okay, so desktop, webinar, data. So these were the original images that we were processing, so getting either mean intensity or doing the negation. And if I go back to the result, which I was putting the negated images in, that DNA1, you see that the images is negated. So this is one way of processing large files. There are three other functions that we have that specifically work on out-of-core images: image file, apply, and image file filter, which are specifically doing out-of-core pixel by pixel operation in case 1 and some local filtering in case 2. This is a paradigm that we would like to extend to all other operations as well that are doing some measurements or doing any global filtering and things like that, not yet built into the system, but coming soon. Questions about convolutions, deconvolutions, and other various functionality for classical image processing. Just a quick response: we do have image convolve and image deconvolve to take care of those tasks, but I would like to also mention that if you go to our homepage or the guide page, main guide page of image processing and analysis, there is a whole suite of about 200 or more functions for doing classical image processing. So for any pre-processing or post-processing measurements and analysis task that you have dealing with these images, you can probably go to the right section, say segmentation, and find various segmentation algorithms in there. A good place to also learn about which function would be more suitable for your algorithm is typically to go to the basic examples. Scope examples are always good starters, but typically we have application examples that show more about what are the typical use cases of that specific function. There was also a question about image displacements and how this can be used. The function image displacements, again, documented maybe not as extensively as it should be, but basically what it's doing tracks every single point in image 1 and sees where it has gone in image 2. On our new in version 11 functions, we have a few examples that show a short video of some cells, in this case, going through mitosis, and then using that function image displacements, we can basically track the movement of each pixel into the next frame of that video and so forth. This is using classical methods for dense optical flow. Typical ones are KLT and far in the back, and we have basically picked from all of those, looked into different implementations and picked one. This one is probably not so relevant for this talk, but we are doing some interpolation based on the displacement. But some other things that might be more relevant, for example, this one is showing a video of some rotating objects here, the windmill. And similarly, we can compute the rotation based on fairly short code that does curl and divergence. This one is doing curl analysis to detect the rotation of the objects, and do some analysis to see where is the concentration of rotation and what's basically a color map or a rotation map of the video that was the input of this operation. With that, I think I'll stop here and see if Marcus would like to answer any of the other questions.
Okay, I just noted a few questions that I quickly saw scrolling through the question list. One question was that about the GPU usage and how the GPU setup is in this case. First of all, for the training basically for neural network functions where it is relevant to use GPU or not GPU, there's always an option. The option is called target device. So if I look under options of net train, you see here the option target device set to CPU. If you want to just work on a GPU, you just have to write GPU instead. So take this over, and then if you have net train, blah, blah, blah. At the end, you just write GPU, and you're working on a GPU. That, of course, only works if you actually do have a GPU, an eligible one at hand. Now, on a Mac, for example, this wouldn't go very far, because what you need for GPU performance or GPU support on a on a Mac is a CUDA capable device. So essentially you need an NVIDIA graphic card, and I, since 2 weeks now, have a kind of a local solution. I bought an exterior an eGPU box, so an external GPU box that I connect via what is it, Thunder wire, what it's called, version 3 connection of up to 40 gigabit per second that it can connect to this external box, and in there I have GTX 1080 Titan card, which allows me to run 3,500 cores in parallel, and that really speeds up the processing in many cases by a factor of 60 compared to my 1-year-old laptop. Okay, so much for the GPU. It's just as simple as specifying target device GPU. Then there was a question in image processing. Quite often what you have to do is scale dependent. So you process for small objects in the image and large objects, and scale is quite a dividing line. So whatever you may pick up with a certain filter in a small scale may not work in a large scale. You would have to resize the filter. So the question is, when I train networks, are they scale specific or not? Well, the answer is that it very much depends on the network or how you build it, because essentially to make it independent, you would have to do it very much like your brain, like your visual cortex does it, and that is run several neural networks in parallel, one working on coarse grain and the other one on fine grain objects, let's say 3 or maybe up to 5 networks doing it in parallel. And then they could combine their output, and that would make your network then scale independent. The next question that popped up is, and that's a classic, is when I was promoting this one neural network for mitosis, this particular one, how do I know how many convolutional layers to take, when to do a fully connected layer, how many channels, so many features to run in parallel, and so forth. Well, quickly up front, a neural network consists of 2 types of parameters. The internal parameters, like the weights here between these neurons or on the neuron connections, or the biases of every neuron, these are internal weights, and they are being trained. So for those, I don't have to worry too much. Hopefully they get trained by the data. If not, maybe they have too many parameters or have other issues. The other problem, though, is I have so-called hyperparameters. These are the parameters that determine how many layers I have, how big the layers are, how many features per layer I take into account, and so forth and so forth. So all the structure. Now, this is essentially, these are the parameters, the hyperparameters of a network that is learned by evolution, at least that has been learned by evolution in the case of your brain. So it's not learned by you when studying, but it's learned or was learned by your ancestors to give a reasonable wiring in your brain and a good setup that allows you to learn to begin with. And unfortunately, it's a little bit the same way currently in the science of neural networks. Basically, if you are new to neural networks, look for a paper that somewhat does what you want, and look at their neural network, and then you can start to deviate. You can try to experiment if you can get away with fewer layers, if you need layers that are wider, more connected, whatsoever. And just by trial and error, you get a feel of what works, because essentially what determines the structure or the number of layers is not the network, it's the data. It's pretty much just like fitting a function. I mean, there's no right or wrong function to fit. It has to be the right function for the data at hand. And that's the answer to that question. And last but not least on my list here, will this notebook become available? Yes, we will make it available to everyone attending, and there will be a download link, hopefully with all the flaws that we still found presenting this here already being fixed. Having said that, and seeing that time is up, I have one final request, and that is we'd like to make a quick survey at the end to see if you like this, if we have pick the topics that were according to your liking or not. And you would greatly help us to improve upcoming webinars by quickly answering this survey at the end of this presentation. That concludes my part. Shadi, anything you'd like to add?
That's it. Thanks a lot for joining us today. Hope you have learned about our capabilities for image processing and neural networks.